by the way, feel free to ask questions throughout. I've got time at the end, but I'm happy to answer as we go. This is a supervisor spec, right? This is a very beautiful, declarative way for us to describe the processes that are going to be running in our Erlang systems. We describe what's going to be running, as you do in declarative systems, not how it's going to be run. You don't see here start child PID X, start child PID Y. You see I want child, in this case, CH3, to exist in the system, and the system takes care of it for us. It's a beautiful, beautiful thing for the lazy like myself. This is another thing you might recognize. This is an app spec. This is what describes to Erlang systems what an application is and how it should behave. The virtual machine at that point takes this description and uses it to start the application. It's a declarative way to describe at a slightly higher level what things should exist in our system. It's one of the beautiful things in Erlang. Finally, we get to the release. This is a Relics configuration taken from a rebar 3 config file. It describes a release. And yet again, we're in this declarative description of what our release should look like, what should be started in our system. Now, each of these steps build up one upon the other, from the supervisor specification for the applications to the application specification to the release specification. But what's next? We're not done by any stretch of the imagination. We've got this beautiful declarative declaration for what's going to exist in the Erlang runtime system, but with a few exceptions for Erlang on hardware, we're not done configuring our system. A large percentage of our system is still not configured. Have you guys experienced this? I suspect you have if you've been running things in production. And we're hitting this impedance mismatch between the language and the system on which the language runs. In the broader context, it's been very popular over the last few years for languages to have their own package manager. Erlang has its own package manager now in hex.pm. Rebar and the Elixir tooling mix both use that. Ruby gems exist as a language-level package manager. Python eggs, Haskell's Cabal, pick a language, it's got a package manager, and there is a mismatch between the packages in that language-specific package manager and the systems on which they run. So in any system, not just Erlang, how do we solve that? There's lots of approaches. On the more simplistic side, we create a tarball, and with the release stuff, and we SCP the tarball over to a box, and we start it up. It's a very imperative, very manual approach. If we're a little bit more sophisticated, we might use a tool like FPM to create a Debian or an RPM, and we might use tools like Ansible, Salt, Puppet, Chef, mostly imperative tools that describe steps to go and install that Debian or that RPM, that Deb or that RPM or what have you, right? And we might bake images, we might not. We might bake Docker containers, we might not. But the fundamental thing that's happening there doesn't really change. And what do we end up with? We end up in side effect hell. Why is that? That's because we have implicit ephemeral dependencies on things we don't control. What are those things we don't control? Inevitably, that is the Debian Foundation's repositories that change and update minor versions of things over time, or Canonical's deb packages for Ubuntu, or Red Hat's Yum repositories. We don't own those, we don't control those, and they change. If I get paged at 3 in the morning, and I put a fix in my system, and I just pushed let's say I baked an AMI yesterday, and I pushed that out. It's 3 in the morning, I fix my thing, I push it into my continuous deployment system, it bakes a new API. What does that new API have in this traditional model? I don't have a clue, neither do you. It might be the same thing I baked 2 days ago with just my change. It also might include an unknown number of changes and fixes that theoretically make the system better, but that happened implicitly without my knowledge, implicitly without my control, without my testing. And it's not uncommon for me to have to spend a tremendous amount of time fixing changes in the system that I didn't expect to solve the actual bug that I wanted to solve. So instead of going to bed at 3:15, I'm going back to bed at 9 p.m. the next day. This side effectness is bad. So what's the solution? The solution is NixOS. And I say that with a certain level of grandiosity, to coin a word or to use a word that sounds really cool. It fundamentally solves this problem. And it solves it in an extraordinarily elegant way. Now, NixOS is kind of a two-headed beast. It is a package manager, a purely functional, lazy package manager called Nix, and a Linux distribution based around that package manager called NixOS. Now, the Nix package manager uses a purely functional language to describe a thing called a derivation. And derivation is a declarative description of a package, including where it's from, the attributes it should have, the dependencies it has, those kinds of things. When it builds, it ensures, and it goes through a tremendous amount of effort to ensure this, that only the things that are explicitly depended on in the expression are available to the thing being built. This is critical. It cleans the environment such that even if you have installed another dependency on the box, it has no access to it. So if you literally cannot have a successful package that doesn't include its dependencies. And finally, packages never change once they've been built. In another way that Nix goes to an extraordinary amount of effort to make sure that packages don't change when they're built. It creates a normal file system for the package, builds that package, and then converts the file system to a read-only file system once the package is built. From the moment of building, it is no longer writable, with caveats about getting into the low levels of the operating system and stuff like that. Finally, and this is the key to some of the beauty of NixOS, it stores all packages in isolation to each other. There's a thing called a Nix store that generally lives in /nix/store, and that's where all of your packages are. And the packages are named with this bit of weirdness here. It's a 160-bit cryptographic hash plus its name plus its version. And that cryptographic hash is not a hash of the sources. It's a hash of every single thing that could have an impact on the build, an impact on that package. It's a hash of the sources of the package. It's a hash of the Nix expressions in the package. It's a hash of the sources of its dependencies and the expressions of its dependencies all the way back to those root dependencies. So that version, in this case, render proto 0.11.1, you could have 20 of those in the system depending on how you set up, how you build each one of those. And it doesn't matter because the true version of the system is that cryptographic hash. And for packages where the dependencies resolve to that cryptographic hash, it will reuse that. If they resolve to a different cryptographic hash, it will use that or build it if it needs to, lazily. It's a brilliant concept. It does have implications, if you can imagine, to the programs that run on the system, because there is no root Linux directory. There is no /bin//sbin /var/lib, these kinds of things. They don't exist. Everything in Nix is managed through the manipulation of the environment, the manipulation of the path, and every application lives in its own unique universe. So now, based on those foundational building blocks, we can step into the declarative description of the system as a whole. So, looking at this, and I know the vast majority of you have not been exposed to Nix, it looks kind of like a function, right? These things at the top, those look kind of like arguments. This looks somewhat, if you squint right, like the body of a function. It's because it is. It absolutely is a function. It's a function that takes arguments from the environment. It returns a thing called a derivation that declaratively describes what needs to be created. So this is actually one from our production systems. This describes a Linux install that has our Thorndike service. We create a Thorndike user, describe the Thorndike user to the system with kind of the normal things, the description, what the home directory should be, the shell it should use. And then we enable the Thorndike service. And we say, hey, use the Thorndike user that we just created for that service. And we create a Linux image in wherever we need to, in AWS or in VirtualBox or in Vagrant or whatever you want to call it, based on this description. And that image will only include the things that are this and the things that this depends on, all the way back to the kernel. That is a powerful, powerful thing. Now, some things to take away from this, things like packages are a namespace. The package namespace contains every single application, every single package in the world. But I'm not installing those. I reference it here. It's passed in, but I'm not installing it. Why is that? Because the only thing I use in that is .bash. It's lazy. It's only going to pull out and build the things that are directly referenced, the derivations that are directly referenced as part of that build. So now I don't get this for free. It's not magic. Thorndike is an Erlang release that I needed to describe as a service. So we can step down one level. And I've had to kind of pull some stuff out to get this sort of on a slide. So this isn't complete, but it gives the crux of it. We have another function here, right? And in that function, we describe our service. And we say, hey, it's a system.d service. Its name is Thorndike. It has a description. I want it to start after the network target. I want it to be used by the multi-user target. And this is the start bit. This is how it starts and runs. So I describe my service to Nix, and it manages how to start it. And then I can make that use of that service at the higher level in my root configuration. And finally, the package. So this is where we start getting into the interesting bits of Erlang. So again, we have our function that returns the derivation. We have this build rebar 3 declaration that supports building rebar 3 buildable things. So if it looks like a rebar 3 and you can build it on the command line with rebar 3, you can build it in Nix. Now this is a release, this isn't a package. It looks a lot like a package, and I've elided the source because it fit on the slides again, right? But I'll go into that in the next slide. I have build inputs. This particular release depends on Bash, NetTools, and Erlang. Those are explicit dependencies. It depends on the Erlang package of lijsx and URI. Those are its Erlang deps. And because it's a release, and so we support Erlang packages, hex packages, Erlang apps, rebar buildable things quite well in build rebar 3. We haven't baked release support into a derivation yet. This is the kind of the first couple we've done. You should see derivation or release support as a derivation in pretty quick order. So I'm going to show you how I did this, but you shouldn't have to do this in the very near future. But in this case, as part of that build, I say, hey, there's an install phase. And in the install phase, I run some things that include make. Now, I'm probably too old for my own good. I run make for everything, and this is just a make file that drives rebar 3, right? In this case, the make target, and I'll show you this in a minute, all it does is run rebar 3 release, create the stuff, and then we have some commands to copy it into the right place in NixOS. Yep.
So you're listing the Erlang package dependencies.
Mm-hmm.
Are those going to have to be mirrored in the rebar config?
Yeah.
Okay, so you have to keep those in sync.
You have to keep those in sync. Now, I'll get into this in a little bit in a minute, and that presents a one problem in that we're humans, we forget to do that, right? So because we forget to do that, unless you're careful, rebar will try to go out and get the releases, right? So on NixOS, rebar 3 is not quite the same as it is in every other place. For the Nix install, we patched rebar 3 to where when it tries to go out to the network, it dies and throws an exception saying, hey, you forgot to put something in your Nix expression. Please do that because that's the way Nix works, essentially. I don't like that for lots of reasons, but it's the best solution we've come up with so far. Yep.
In the same way with, for example, field inputs, they don't have version specified?
No, so I can show you this. The way Nix handles everything is in a file system, in a Git repository. So there's a, here, that might be hard. In the root thing is a list of all the current names of packages in Nix. And they're not, think of names of packages in Nix much less like package names and much more like bindings. It's a name bound to an expression. So it's very, very common in Nix for names to be bound to a specific expression without a version, as that is the current latest version in the Nix system. And then where we have multiple versions of the Nix system, you'll see name underscore version or name dash version, and that way you can use them as needed. But this is the most common idiom, where you keep your kind of Nix as a living system and rely on the names of the things that they are. It's not, because all references are hard in Nix, there is no constraint solving, there's no dependency change without you explicitly going in and changing the Nix expressions. This will always resolve to the same thing, given the same kind of commit hash in the Git repository in which Nix lives. Does that make sense? So I'm going to talk about this in a second, but this is one of the fundamental differences in Nix versus other systems.
So somewhere in the configuration, you're saying LE version something?
Yes. Okay. Yeah, and I'll show you that in a second when I swap over to do some terminal stuff. So this is what a more normal expression looks like. You see it looks pretty much like the last one. The only thing we have done is we don't need a separate install phase. Rebar 3 derivation understands how to build and install Erlang OTP apps built with Rebar. So we have the same kind of arguments we have. In this case, we're doing LE. We need std-env from the Nix environment. We need fetch from GitHub because that's how we're going to get the source. And we need to build Rebar 3 derivation. We name version, pretty straightforward. Here, we're doing fetch from GitHub. Nix knows how to fetch from GitHub. It's quite common. With the owner, which is the organization or owner of that GitHub repository, the name of the GitHub repository, the reference, and you can often use the refs, the actual version number in there. In this case, there wasn't a direct correlative version number, so I had to use the commit ref. And then finally, the SHA of the tarball that's going to be pulled down. Now, this is not the same as the cryptographic hash we saw earlier, but it does roll into that cryptographic hash. It ensures that the tarball we get, just like any kind of hash, right? It ensures that the tarball we get is the tarball we expect to get. And then the Rebar 3 does the right thing for your world. So this very clearly bridges the gap, that declarative gap between the Erlang virtual machine and the OS world as a whole. Yep.
Do you write all of this by hand, or do you have anything generated from whatever you have?
So I'll talk about it in a second. So yes, on both. For many of the existing packages it's generated, there are certain ones that I'll go into in a minute that we can't generate for various reasons, and you write them by hand. And of course, the ones you use internally in your company for now are written by hand. Fortunately, it's fairly straightforward to write by hand. I was having a conversation some time ago where with a person, I was talking about NixOS. And I have to say, like, it has solved enough of my problems, both from a kind of a management perspective and to some extent from a security perspective, that I'm a bit of a fanboy, right? And I was having a conversation with a kind of more traditional guy who's done lots of work with Red Hat, lots of good work with Debian. And the conversation went something like this. I was like, you can do this thing with Nix where you understand how your dependencies change over time. It's in a repository. You can use the same tools to manage your source of your system configuration as you can to manage all your other source. It fits into your existing development pipeline. Your versions are controlled. You only pull in what you need to pull in. And the response was, well, I can pin my dependencies in Debian, so that'll work for that. And I can do this, and it'll solve my problem. And it reminded me quite tremendously of conversations I've had with imperative programmers talking about functional languages, right? People with a Java background or a Ruby background or what have you. And that kind of moved me into the mindset of, there's a guy named Paul Graham. He's famous for Y Combinator and originally for VOWeb. And a while back, he wrote a blog, and he posits this thing called the Blub paradox. And this is a bit self-serving for folks that are functional programmers, I have to admit, but I think it's actually accurate. And the crux of the paradox is that For languages that are higher on the curve of power, Erlang, Haskell, these kinds of things, users of that language can look at languages that are lower on the curve of power and understand what makes that language more powerful, understand the things that makes it more productive, more syntactically terse, these kinds of things. But for users of language lower on the power curve, the C, C++, Java, Python, Ruby, what have you, they don't have the ability to look up the power curve and understand what makes those languages more powerful, because they haven't used them, they haven't grokked them, they don't have a full understanding of it, and they're outside of their experience. So a person's transition from using one of those languages lower on the power curve to using a language higher on the power curve is almost a leap of faith. In the vast majority of cases, the reason a person makes that leap is because they heard a talk by someone they respect, or they wrote a book, or their friend has gone off and taken that leap before them and convinced them that they need to go ahead and spend the time and the energy to learn it. And once they've learned it, they can look back and say, oh yeah, you were right. This was worth it. For the first time, I think there's a power curve of system. Hopefully that comes back. A power curve of system management, right? Where, pick your language. I'm a huge fan of Ubuntu. I've used it almost since it came out. But Ubuntu is lower on the power curve from the perspective of production systems than Nix is. So I can articulate all of this to you guys, and it's probably going to be interesting. It's probably going to sound cool. But you're going to be thinking in your head, I suspect for the most part, like, yeah, but it doesn't really buy me much over what it is that I'm doing now, right? And my thing that I'm positing to you is, it does take the time, like, take my recommendation, walk away, use it enough to understand how it's better, and that leap of faith will be valuable to you in the almost immediate time frame. Oh. Sorry, guys, I'm off in the weeds. Okay, so now we're going to come and talk a little bit specifically about Erlang support in Nix and how that works. So it kind of composes of two parts. One is support during the build of an Erlang package itself, and the other is what Fred alluded to, which is pulling in packages from Hex repository and making those available. So we have the somewhat unfortunate problem that Rebar 3 really, really wants to own the dependencies super badly. It doesn't want to give those up for anything. So we have to do some things that kind of trick Rebar 3 into thinking that it has owned the dependencies and it's already pulled them down. And then we still had to go and patch Rebar 3 to force it to never pull down dependencies. One of the really important parts of Nix is hermetic builds, basically builds that do not reach out to the network and pull and change during the build process. And in the various build servers, they actually make sure that doesn't happen by using things like chroot environments and those kinds of things. So we had to make it hermetic. So we wrote a little tool called Rebar 3 Nix Bootstrap, which is actually an e-script that the build Rebar 3 derivation goes out and runs previous to actually calling Rebar 3. That derivation looks at the Nix kind of Erlang environment, creates a symlink farm in the _build directory in the right profile, and then and make sure that matches what Rebar 3 expects, and then Rebar 3 can be called. It's actually pretty straightforward. In some cases, it may have to manipulate the Rebar config, and it'll make a copy of that and point Rebar 3 to the copy. And that's how kind of we support it. It's not optimal. It does what it needs to be done. Rebar 3 functions as you would expect to function. Packages that can be built with Rebar 3 off of Nix can be built with Rebar 3 on Nix, but this is the bridge through the hermetic builds that we needed to make Rebar 3 function. The other side of that was the Hex to Nix tool that we wrote. And basically, Hex to Nix goes out to the hex.pm, pulls in the complete graph of packages, generates, sorry, I lost my train of thought, generates Nix expressions and actually makes use of John Hughes' pretty printer stuff because it actually does work quite well. And it also looks at the dependencies, and it uses the exact same algorithm that rebar 3 does to resolve the dependencies so that they match what rebar 3 expects. Now, it doesn't actually use the same code because that code's not been exposed to be used as a library, but basically uses the exact same algorithm. So we generate that. We attempt to build those, and in a fair number of cases, they don't build, and they don't build for a few different reasons. First off, people forget to specify their dependencies. They'll push stuff to hex. They don't specify their dependencies. In Nix, things don't build without their dependencies fully specified. So there's a fair number of packages that need to be fixed in hex.pm. Second problem, there are native extensions in a bunch of hex packages that implicitly depend on libraries being available in the OS. They don't expose that. I mean, you as a human can go and look and read the readmes or the documentation and see, oh, it needs, libnotify or something like that. But there's no way for us to algorithmically detect that. So those packages essentially don't build. There's some solutions to that we could get to in the future. And finally, there are packages that are just broken. Or one thing we don't support is old-style rebar Git dependencies. For some reason, we have not been able to convince rebar 3 to accept what we get put on disk as there, and it will inevitably go out and try to download those regardless of what we've done to try to convince it otherwise. That's something we'll probably fix in the near future, but for now it means that some proportion of packages don't build. But the vast majority of packages in Hex are on NixOS and available right now. So let's see if I can do this in my somewhat funky setup. Can everyone see that okay? So we're going to go into this is a Erlang release. It looks, and this is a Nix. So my laptop, yep, I can. Yeah, that's going to be really annoying, is it not? Okay, cool. So this is a very standard rebar compatible release that could be built on any system. It looks exactly the same on Nix as it does anywhere else. The only real thing that is different is that shell.nix over there in the corner. That shell.nix is a derivation that I'll show you right now. It's a derivation that describes kind of the developer time description for Nix. And essentially, it says the same things that we were saying otherwise. Now, here's the interesting thing. That shell.nix is a file that lives in that repository. Every time I run make, well, you can't see it now, but I run Nix shell. Here, let's do something that's a little bit more, sorry, guys. How do I get it back? That's proving to be rather interesting, is it not? That's tremendously annoying. There we are. Let's do this. So this works a little bit better. So we run Nix shell. Nix shell is a way to use a piece of NixOS combined with a derivation in shell.nix to build a closed environment over your current directory. So inside of nix.shell, I've specified this pure argument, and that pure argument says don't make anything in the surrounding operating system available to it. Only make the things specified in shell.nix available to it. Does that make sense to everyone? So I do that, and then inside of that environment, I run my Erl command. So I have an Erlang REPL that only has access to the things that I've specified in that derivation. Now, I run everything inside this Nix shell. Oh. So this is the make file, and all it does is drive, and this is kind of a convention on my part. I wouldn't say it's any kind of Oh, what's going on? Oh, yeah. So we come down here. And everything we're doing is inside this Nix shell. Every make command we run, every REPL we run is inside of Nix shell. That means that my package manager is a part of my development environment. My package, the package that I'm going to deploy with, is the thing I live inside during my entire development process. Right? That's a powerful, powerful thing. Because Nix lives in a set of files, in a directory tree, it lives in a Git repo, I have a local copy of that repo that my Nix environment has pointed to. I manipulate that in the context of my running world, and I can build my systems on top of that, my development systems, as if they were production. Now, we, internally in my company, we have a little bit of tooling that allows us to do that trivially, but with a single command, I can spin up a group of VirtualBox images running packages built from my development environment, but built with the packages that they're going to run in production. Built with, in the same exact way that they will be when they run into our continuous deployment environment. And I would say, like, more than anything else, that is the power of Nix. Now I've got time for questions. Yeah, Fred.
Yeah. So what motivates you to, for example, mock the entire hex thing rather than calling something like rebar3 lock and then just packaging all the source files already in place?
So this is one of the approaches that a few other languages have taken. Almost inevitably, they've moved from that approach. A great example of that is the early versions of Elm support in NixOS did that exact same thing and then moved away from it. And my suspicion is they moved away from it because when you close over that particular set of packages, you basically have a kind of a binary set of, it's not binary, but you kind of have a binary closed set, and your systems have the potential to become disjoint, right? So I have one release that closed over its set of things. Even though they're on the same head of Nix packages, they're running different versions of their dependencies. It's my suspicion. I looked at what the language has done historically and saw their change over time, and I just went straight to pulling in the packages directly. Yes?
So, I get the concept,
Mm-hmm.
I like the idea of the functional configuration
Mm-hmm.
management, and it's carrying it all the way to OS, but I'm getting a particular OS called NixOS.
You are.
Now, I don't know anything about it. It's, I assume, based on some version of Linux somewhere. But what if I wanted a different version of Linux, but still wanted or I wanted something like I have to like hardened BSD. I'm guessing it wasn't based on hardened BSD.
No.
What is it based on, and do I have choices?
So it's not based on any existing derivation of Linux. It's not based on Ubuntu or Debian, any of those kind of things.
Based on some set of source code.
It is. It's based on Linux kernel and the GNU user space as packaged by Nix. If you don't want to use that, you don't have to. You can use the Nix package manager and get 90% of the usefulness of this. It won't carry the dependencies down to the kernel level because it has no control over that. But everything above the kernel level will be controlled by Nix. So you could use hardened BSD. Well, I know you can use BSD. I suspect you can use hardened BSD and the Nix package manager, and it would work just great, with the caveat that the dependencies don't go all the way to the kernel. You can use Mac. Now, there's not as many packages supported on Mac, but you can do Mac development inside of the Nix package manager, and everything I just showed you works perfectly aside from the host configuration. You don't get that because that's NixOS, not Nix package manager. But you can still, you can actually still build images from a configuration if you wanted based on NixOS. So you get a large percentage of the capabilities without having to shift to an operating system that you are not familiar with. Other questions? All right, then, yeah.
Oh, sorry. So the operating system that gets built has a very minimal number of packages. The exact number of packages needed to support the derivation.
Yeah, the root configuration, essentially. Okay. So it is the kind of like when you're building a release, you have that root app, and Relics includes all of its dependent apps. NixOS does the same thing, but for your entire operating system.
Okay, and you have generation targets, so you can generate an Amazon AMI, you
Yeah.
Okay.
Yep. So there's some caveats to that, and this is where we go from like theoretically wonderful to kind of real world stuff, right? So Nix has a lot of tools to generate images directly from a configuration, and I really, 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 really want to use those tools badly. But generating, for example, an Amazon AMI directly from a Nix configuration is a bit of black magic. Not so much from a Nix perspective, but getting it to run happily in Amazon is very difficult. And from my understanding is that is true regardless of what operating system you want. If you want to come from a virtual machine to get it running in Amazon's AMI, it's interesting. So the hack for that is you take an existing base kind of version of installation of NixOS, you put your configuration on it, you run NixOS rebuild switch, which is the command you use to rebuild the operating system, and it goes and forces that install to look like your configuration. Then you run garbage collect and you kind of get what you want without building the image directly. So in our continuous deployment environment, how I want it to look, how I'd love for it to look is Nix configuration, run Nix build, which is a kind of a way you can build without installing Nix commands to build the image, and then upload the image to Amazon or wherever, right? What I actually have to do is use Packer, which is a brilliant and a good tool let's just not worry about it. Use Packer to build which is a brilliant and good tool to build the image. Use the shell provisioner to copy my configuration over, and then run NixOS rebuild switch and the garbage collection of Nix packages that are no longer relevant to create the AMI, and then have Packer bake that AMI for me.
Okay.
Yes?
How do you deal with, say, per host and big that might be different per host?
So there's a couple of different ways. There's an option in Nix to pull the configuration from the AMI user data if you want to. I don't have a lot of experience with that because we take the approach of kind of ephemeral infrastructure. We have a single configuration for all of the kind of homogeneous hosts, and if we change configuration, we rebuild the AMIs and republish them. So I know it's possible. I can't really point you in the right direction there, unfortunately. Yep.
Is there a way to build a tree of version dependencies, just the latest version of these dependencies, and be generated automatically? That's something that's doable.
So for a lot of the packages in the system, let me see if I can get out of. So for a lot of the packages in the system, they do that. If you look at the Haskell support, which is stupendously good in Nix, all that's generated. For example, the Erlang dependencies, the vast majority of those are generated from Hex, and every time we do a new release, every time they do a new release of Hex, we make sure that they have a new generation of the Erlang packages. A lot of packages, though, are also hand-built. The packaging itself, the community maintains kind of those package declarations in the same way that the Debian community does for Debian packages. The one difference is because that lives in the source file that I own that sits in my repository, I can change those if I need to and modify them and add patches and those kinds of things. A great example of this that's kind of off the beaten path is recently there was a vulnerability to glibc. You guys familiar with that? Really, really scary vulnerability. In our system, and this is granted, our systems we're a young startup, right? We don't have a lot of things deployed, but the time from when I became aware of the vulnerability to the time it was fixed in production was about an hour. Pull in the patches, push it into our CD system, Nix rebuilds it all, everything that depends on it, which took most of that hour, and then gets redeployed into production. Doing that same thing in the same time frame with the more traditional approaches is very, very difficult. Not impossible, but very, very difficult. And that I think that's another one of the clear values of Nix. Other questions?